elements that are on the left-hand side of the periodic table, okay, has to come first. So now when you are combining, obviously with a compound, with the formation of the compound, there has to be an two elements, two or more elements. Now the one that appears on the left-hand side of the periodic table will have to be come first, meaning that we pronounce it first before the other one. Now that then took us back to understanding the periodic table itself, to say how is then these elements positioned the way they are in the periodic table. What are the ones, or what do we refer the ones that are on the left hand side? What do we refer the ones that are on the right hand side? What is the ones that are in the middle? Okay, so that we understand how they behave and we understand their properties and all of that, which we'll come to it in just a second. Okay, now to name compounds of the elements, for example, with sodium, potassium, chlorine, iodine, we needed to follow certain rules. Remember, we said that the ones that are on the further left, okay, will then come first. Hence, we came up with the name sodium chloride, when now sodium is chemically bonded with chlorine. Okay, so we couldn't not say chloride or rather chlorine sodium. Okay, why? It's because sodium is on the further left hand side of the periodic table as compared to what? As compared to chlorine. So sodium had to come first before chlorine. Same thing goes with potassium iodide. Okay, we could not say iodide potassium because potassium is on the further left, or is a further left of the periodic table as compared to the iodine. Okay, so this is what we're talking about. This is the periodic table of elements that we're talking about. So I like it because it's very detailed. It just simply tells you all you need to know about the periodic table itself, about the metals, why they're positioned the way they are. Okay, so this is, as you go down, these are the groups. Okay, so you've got group 1, group 2, and group 3, group 4, up until group 12, and then right over there you got group 13, group 14, 15, 16, 17, and then 18. Okay, as you can see, we've colored them using the different colors so that we understand which ones are metals, which ones are non-metals, which ones are semi-metal. Okay, if we look closely to it, then you'll see that group 1, group 2, okay, and all of the ones that are on the further left, group 3, group 4, group 5, those are metals. All right, so they are found on the further left hand side of the periodic table. But if you go onto the right hand side of the periodic table, which is that side, you'd see it as greens. So you've got your semi-metals being in yellow. Okay, here's our semi-metals. And then you've got your non-metals in green. Okay, and then you've got your halogen in a very much darker green. Okay, and then you've got your noble gases as in what? In blue. Okay, here are your noble gases over here, and here are your halogens. Okay, and then these are then your what? Your non-metals. These are your metals, different types of metals. Okay, and then you've got your semi-metals in here. These are in yellow. Okay, so I'm just going to include them right there. These are your semi-metals. Okay, so knowing that now on your further left is your metals, on your further right is your non-metals, they are closely linked with your what? Your semi-metals, and then on the last grouping is your noble gases. Okay, now in each of them you're going to see a symbol, okay, symbol that represents that specific element, the atomic number, the atomic molar mass of it, and then all of the details pertaining that particular element. Okay, now why is this important for us to understand the periodic table? It's for us to be able then to name the compounds correctly. Okay, so as we said that on with the element that comes on, or rather that is positioned on the further left, okay, in a compound is the one that will come first, and then the other one that is positioned on the further right hand side will then come last. Okay, your tri and are used to name the compounds that have 2 or 3 atoms of the same element. Okay, For example, there will be your carbon dioxide. That di indicates that there are two atoms of oxygen. So as you would write the molecular formula for carbon dioxide, you'll say CO2. That means there is two of what? Two of the same atoms of what? Of oxygen, okay, in carbon dioxide. And there's will be your sulfur dioxide, okay, sulfur dioxide, all right. That is where we use our prefixes to indicate that there is more than just one of the atom of the same of the same element. Okay, there's another one that we made of sulfur trioxide. Now your sulfur trioxide would look like something like this. Okay, because tri means three, di means two, and then one means mono. Okay, mono means one. Okay, di means two, and then tri means three. All right. So now sometimes the rules are not applied. Okay. For example, the best example to use is that of calcium chloride. Okay, where it should be we name that it's calcium dichloride. Okay, why is that? Because there is two of chlorine atoms that are there. Okay, but it is just named a calcium chloride. Okay, instead of dichloride. And then another one will be your iron chloride, okay, which is your ferric chloride, even though it should really be named called iron trichloride because of the three atoms of chlorine that exist there. Okay, however, we just refer to it as what? As ferric chloride, okay, which is used for the printed circuit boards. All right. Now, when naming compounds, we usually end with an "ide" at the end, with an "ite." Okay, for example, in sodium sulfide, okay, with an "ate." For example, in what? In copper sulfate. Okay, so that helps us to just show the combination of the two elements that have combined together. Okay, now in this activity, we need to then know how to then name these compounds, to give the names of the compounds. If you are given a formula, you are giving the name, or if you are given the name, to be able to give the formula by looking at the name, then going back to your periodic table to say, okay, what is this the symbol standing for, or it's standing for a carbon, or it's standing for oxygen, then you are able to then give the names to that particular compound. All right, but even before you do that, here's our learner activity 1. It says that identify whether the following pure substances are elements or compounds, because even before we can name them, okay, we should be able to identify between that of an element and the ones of the compound. So when they say identify whether the following pure substances are elements or compound, what is it that's going to give us a clue? Okay, once now we see more than one element, okay, these elements being two or more and chemically bonded to each other, okay, then we know it can't be just an element, but it has to be a compound, because a compound has two or more elements that are chemically bonded to one another. The first one is oxygen. Okay, now there is oxygen in the periodic table. Oxygen can just exist in its purest form, okay, in its simplest form. So oxygen is just an element on its own, okay, because it's not bonded to any other element. So this one will there be an element. Then the second one, it is nitrogen dioxide. Okay, so now we have nitrogen. Also, we've got di. Okay, that means we've got two of what? Of the oxygen. Okay, nitrogen dioxide will then be what? A compound. Okay, because now I've got nitrogen and then two atoms of what? Of oxygen that are chemically bounded to each other. And then the next one will be your sodium chloride. Okay, again, you've got sodium existing in its natural form alone. Now, in this case, it is combined with chlorine, and therefore together they form a compound. So this one is a compound. And then the next one will be your hydrogen sulfide. Again, you've got your hydrogen, and then you've got your sulfide, a compound once more. Mercury. There is mercury. Mercury is just an element existing on its own. It is its purest form. It is not combined with any other element. So mercury is an element. Potassium. Potassium again is an element. So what helps in this exercise? It is knowing, okay, the elements of the periodic table, okay, knowing how they exist in their own form before they are able to be joined, okay, with another element. That helps as well, okay, so that you can tell, oh, this one is an element and this one is a compound, because there is more than one of the element that is joined to it, okay. Moving right along on the activity 1 still. Now we still have 1.2 says identify the substances that are pure. Which ones are pure? Okay, they exist in its simplest form. Okay, now we've got steel, we've got smoke, we've got table salt, we've got starch water, we've got brass, washing soda, rust, baking soda, Epsom salt. Okay, remember, pure substances can be elements and can be compounds. Now let's look at what? The steel. Steel will have to be pure, okay? But the smoke cannot be pure, because on the smoke there are so many gases that are in there, okay? So it's not pure because it's made of a combination. Like right now, there's just carbon dioxide, there's exhaustion from the car pipes, there is oxygen right in the midst of the atmosphere, okay? So the smoke cannot be a pure substance. So we can take the steel, we can take the table salt, okay, because it is your sodium chloride, okay. It is existing in its purest form because it's the simple type. You cannot break it down even further, okay. Starch water, not so much, okay, because now there's just a mixture in there, okay. There's a mixture of starch and then of water, okay. So we said no to smoke. We are also saying no to starch water. Brass, yes, no, we're just saying no to that as well. It is a mixture. Washing soda, okay, yes, it can exist in its purest form, okay, so we can take this as being pure. Rust on its own, alone, it can be existing in a pure substance. Baking soda, yes. Epsom salt, and then another yes, okay. So from the list that you are given, it is important to just identify if there will be mixture of more than just that specific combination, okay, of the properties now change. It can be broken down in further. So there's a mixture. So you have to be able to differentiate between a pure substance and then a mixture of things. For example, if you were to take let's take from the list of ours and say table salt, okay. Now if you take your table salt and then you compare it with what, with your smoke, okay, your smoke is just definitely diluted with so many other gases apart from the one that you would like. In as much as we breathe in some other gases that we shouldn't be even taking in. But with table salt, there's just a specific ratio of sodium to chlorine ratio that is chemically bonded to each other, even though it is a compound, but it's still regarded to be a pure substance. All right. And then with our activity 2, based on what we mentioned about how to give the names to the compounds, all right, it says the instruction here, given the names, write down the formulae for the compounds below. Okay, so we are given the names of these compounds. However, now we need to give the formula for these ones. How can we write the formula of these compounds? Okay, the first one is magnesium oxide. Okay, then there's a magnesium in there, there's oxygen in there. Okay, so this will be our magnesium oxide. Okay, and then the second one being carbon monoxide. Remember what we said about having the prefixes that we use. We said we can use mono, we use di, and we use trioxide. Okay, now with mono means 1, and then di means 2, tri means 3. Okay, so in this case we've got mono, so it's just going to be carbon that is chemically bonded to oxygen, one oxygen, that is. Okay, however, when you look at carbon dioxide, okay, that means there are two atoms of oxygen, okay, that are chemically bonded to what? To carbon. So this is going to be then CO2. All right, and then we've got sodium oxide. Okay, sodium oxide is then given as Na2O. Okay, and then the last one, it is sulfur dioxide. Therefore, sulfur dioxide then is going to be written like that. Okay, so please just get used to writing, moving vice versa, whether you are given the name, writing the formula, whether given the formula, moving right back to giving the name of that particular compound. Okay, just look at the chemical composition of that particular compound and then you're good to go. All right, that is why on this second activity, again, given the formulae, now we need to go back to giving the name. Okay, now MgO, we just did that one. It is your magnesium oxide. CO, now because there's only one oxygen that is there, is going to be carbon monoxide. CO2, okay, carbon dioxide. Na2O, this is your sodium oxide, okay, and then Fe2O3, this is your iron trioxide. Because of the what? Of the three, okay, three atoms of oxygen that is there, okay? And because of you want also to indicate the valency, it is important to just indicate that it is iron trioxide. This is indicating the valency of the what? Of the iron itself, okay? Now let's move right along to cations and anions. How are they formed? How they become to be, we call it cations and anions. Remember, all of them are just ions, okay? Now, cations we refer to positively charged ions, okay? And then anions we refer to the negatively charged ions. These attract one another to form a neutral compound, okay? But when we take this compound, okay, put it in water or in any aqueous solution, what happens is that compound ionize. To ionize is to dissociate completely in water and then form these positive cations as well as what? Negative anions, okay? So when they just exist as compounds, they will not show those specific charges because they exist as neutral. However, when you put them in an aqueous solution, these ions then will form positive cations and then negative anions. Now, the cations are of the metal atoms, okay, which are the ones that we said they are on the left or the far left hand side of the periodic table. And then the anions are the ions of the non-metal atoms, okay, which are on the further what? On the right hand side of the periodic table, okay? So why is that? Now, the formation of cations and anions are due to the fact that your metals will lose the electrons very easily, okay? And then the non-metals, they gain the electrons very easily. So it's pretty much your oxidation reduction kind of thing, okay? So the formation of cations and anions is because your metals just tends to lose the what? Their valence electrons easily, and then the non-metals will then gain those electrons, okay? Hence then these ones are more negative because of the gaining of more electrons on the other side, on the non-metals, okay? And then the positive because they lose the electrons. When they lose the electrons, they become positively charged, Okay, I always make an example that all the time what move is your electrons. Whether the electrons have been lost, okay, let's make a typical example. Here's my object. This object was neutral at first, so I'm just going to make protons, 3 proton and 3 electrons. All right, so once now this object of mine loses 2 electrons here, this object will then become positively charged. And why is that? Because it is seeking for these 2 electrons. So there is protons that are not bonded to any other electrons. So there are 2 electrons that are looking for their partner, which are what? Which are electrons, because these electrons have been lost. This is in a case where they are lost. So then what will be the charge on this specific object? The charge on this specific object will then be 2 plus, because I have got 2 electrons that are wandering and lingering and seeking for their partners. Okay, let's do another. So this one is positively charged, so this is a what? A cation. Same material, okay, was neutral, meaning there was a balance, there was equal number of protons as well as electrons, but now had gained, let's say for example, 2 more electrons. Okay, so now this object of mine have got 2 more electrons that it has gained. All right, so due to the extra gain, okay, even though it is happy, it has gained electrons, however, now there are electrons that do not have the protons partnered to them, so it becomes negatively charged. Okay, so which charge will it have? What charge will it have? It will have a 2 minus. What does this mean? It means that I have 2 more electrons. And electrons, because they are negatively charged, so it's going to be indicated as negative. So there's going to be formation of what? Of anions. Okay, so because I've got now 2 electrons that I've gained, so that means I've got an excess of electrons. There is no in any way that I have spoken about the moving of protons, because protons are embedded inside the nucleus and it's not easy for them to move. Now what easily moves are the electrons, the valence electrons, which are able to then be given off or be gained easily, okay, due to the interaction of objects. Okay, now the charge on simple ions can generally be deduced from the group number in the periodic table. So that means then we can tell that because this specific element belongs in this group, it will behave in this manner. It is likely to lose electrons, or it is likely to gain electrons. How? So we've got this nice table that indicates the group number as well as the likelihood of that charge in all of the elements in that specific group. Okay, so let's look at group number 1. Group number 1 will have a charge of a positive 1, and it makes sense because on group 1 we've got the metals. Now the metals, they easily lose electrons. When they lose, they become what? Positively charged, so they become cations. Okay, and then group 2, and as well as what? Group 13 as well as group 14. Okay, now group 15, because they are on the non-metals, they gain electrons. They have more, they'll have excess of electrons. Hence they're going to become what? Negatively charged. And when they become negatively charged, their charge will be -3 on group 15, and then on group 16 will be -2, and then group 17 will be -1. Now your noble gases are known to be the ones that are mostly stable. Okay, so they do not have a charge. All of the elements just wish they could be like what? Like your noble gases. Okay, so these are the charges and their likelihood depending on how they are positioned on the periodic table of elements. So your group 1, your group 2, group 13, 14, 15, 16, 17, 18, 19. So we don't have a 19, 17 and 18, because your 18 will be your noble gases, and then your 17 will be your halogens. Okay, now Continuing with your cation, you'll see that sometimes we use Roman numerical. Now, next to the name of the cation is used, so we indicate the valency of that specific ion. How? So, for example, we have copper chloride, and you see that there's a Roman figure 2 there. Copper 2 chloride. What does that even mean? It means that the valency of the copper in this case will be 2 plus. Okay, it will be 2 plus. So it indicates the valency of that specific copper at that time, because we do have a copper chloride, copper 1 chloride. Here is how then we'll indicate the valency of that specific copper. Okay, it will be Cu plus to indicate that, okay, it is short or it has lost, okay, 1 electron, and then this one will indicate that it has lost 2 electrons. Okay, what we refer to this is your stock notation. Okay, to say, okay, they are both copper, but this copper, depending on the element that it has bonded to, okay, then it has lost, or it has shared 2 electrons, or it has lost 1 electron. Okay, so this process of then entering the Roman numerical, okay, to indicate the valency of that specific ion, we refer to it as a stock notation. All right, so these are the cations that we'll have. Bear in mind, okay, the grouping of these elements in the periodic table. Bear in mind which ones are metals, which ones are non-metal, which one are semi-metal, okay, or metalloids in that case. So these are all the list of the ones that will be cations but have lost just 1 electron, have lost 2 electrons, have lost 3 electrons, have lost 4 electrons. Okay, and how they'll behave will depend on their chemical bonding. These are also the list of the N ions. Okay, remember, N ions are mostly your nonmetals, and they gain electrons. They become more negative because they've got excess of the negative charge, okay, which is brought by the electrons that they've gained. Okay, so you've got your negative 1, you've got your negative 2, and then you've got your negative 3. Okay, remember, we've got group 1, group 2, group 3, group 13, 14, okay, and then 15, 16, 17, and 18 with those charges that we have said. Now let's try looking at the ions that we've spoken about and how they come about to become cations or anions. Now let's just give the names of these following cations and anions, because there's a mixture in this list. So the first one is H plus. So you look at the element, okay, which element is being given in there. So this one is a hydrogen ion because there's a symbol for hydrogen. This one is a lead ion. This is chromium ion, and then this is hydroxide ion, and this is calcium ion. Okay, so some of them will be your N ion, like for example your hydroxide ion is an N ion because it is negatively charged mostly, you see. So now let's look at the chemical balancing of the equation. How do we balance chemical equations? What is it that is important to look for when we are balancing the equations? Now it says that Hg is the symbol for mercury, which is very true, okay? And then O is the symbol for oxygen. Now when these two elements react with one another in a chemical reaction, there's a formation of a new substance, okay? And we're taking it slow, right? Now, that new substance that is being formed is what we called a product. Now, when we are reacting mercury and oxygen, those are our reactants. So reactants will react together, okay, in a chemical reaction, and then they will produce a product, all right? So how do we then write this in a chemical reaction? We can write it in a chemical reaction to take place in the form of showing the reactants being on the left and then the product being on the right. And these are then separated by what? By an arrow. An arrow represents the reaction taking place from the reactants, okay, to, because it has an arrowhead on it, okay, just like we did when we spoke about the forces, the arrowhead. It shows the direction in which the reaction it is moving into, okay. So when we then write an equation, we count the number of atoms on the left, on the reactant side, and then we count the number of atoms of each element, okay, on the right hand side. So we look at the reactants, and then we look at the products, and we then try to balance these the number of atoms of each element, okay. So let me just show you how then a reaction would look like. So you've got your mercury, it is reacting with oxygen, okay, and then it is forming mercury oxide. All right, so now what has happened is that this side are your reactants, and this is what? Your product. So this, in the middle of it, it is showing the reaction in which side it is going to. So for us to be able to balance the chemical equation, it is important to look at the number of atoms in each element, so we make sure that it is the equal both in the reactant part as well as in the product part, okay. So when you look at now, because this one is balanced, when you look at the mercury, now mercury, there are 2 atoms of mercury, as well as they are reacting, these 2 atoms of mercury, they are then reacting with 2 atoms of what? Of oxygen. Therefore, it is important to then balance then the number of atoms on the product side. So to mean, say this number, okay, then is multiplied into whatever element that is in there. So 2 times of the mercury, that means that there are 2 atoms of mercury, and also 2 times that of oxygen. Okay, so that means that we've got 2 atoms of oxygen even on the product side. Then gives us a well-balanced chemical equation. Okay, so you can break it down and write it in steps to say this side with my mercury I've got 2 atoms, and then with oxygen I've got 2 atoms. Here I've got, for silver I've got 2 atoms, oxygen I've got 2. Oh, then my equation is balanced. Okay, so it is also important to note that you cannot then add a subscript number, okay, right at the bottom. Okay, the only number that you can add is the one that is pre the element, just before the element. Okay, now we cannot add the one that is of a subscript. Okay, so that the number that we add before the element can then be multiplied throughout the specific element, or rather compound, depending on the case. Okay, now let's put that into action. Let's look at sodium that is reacting with oxygen to form sodium oxide. Okay, so how can we balance this? Remember, right now, as of it stands, the number of atoms for sodium is just 1 on the reactant side, but for oxygen I've got 2 atoms. Okay, and then on this side I've got, for sodium I've got 2, okay, and then for oxygen I've got 1. So you ask yourself, how can I balance this then? Okay, so we can say we add 4 for sodium, okay, and the reason why, let me add an arrow over here, the reason why we're adding 4 atoms for sodium, remember we cannot add a subscript number, only just a number before the element. Okay, so let's balance the sodium. Let's deal with sodium only first before we come with to oxygen. So we've got Na2. Okay, so remember I cannot do anything with that 2. Okay, so but I can do add. Let me just try and use a different color. Let me add black. So what we did here, we added a 4 here, and on this side, if now we've got 4 atoms of sodium, how can we make this one to be 4? By adding a 2 over here. So that when you say 2 times 2, it gives us 4. Now, with sodium we are done. Sodium, we have 4 atoms on the reactants, and then we've got sodium having 4 atoms. Okay, then it is shown to be plus what? Plus O2. Okay, bring it back, and there was an oxygen in here. Remember, with this number that we insert here, we multiplied throughout the elements in that specific compound. So this then means that it's 2 times sodium, okay, which is 2 atoms of it. Then it gives us 4, and then 2 times that of oxygen, it gives us what? 2 again. If you look at this side, we still have 2 atoms of oxygen, which is oxygen is equals to 2 atoms. Now it is balanced. Okay, so what you usually mark allocation will be mark allocating the reactants as well as the product, and then you being able to balance everything down. Okay, so please pay attention to the number of atoms in the reactants as well as in the product. Okay, let's try another one. So we've got iron reacting with oxygen to form iron trioxide. Okay, now what is existing there now? We've got iron have 1 atom that is on the reactants, and then we've got oxygen, there's 2 atoms. But when you look at now at the product, you've got 2 atoms for iron, and then oxygen you've got 3. What can we do here? Let's do something. So I'm just going to start with iron. If I add 4 here to make then iron to be 4 atoms of iron, okay, let's fix on the other side. How can I add, or how can I make iron to be 4, or rather to have 4 atoms? That means I have to add 2, okay, because your 2 times 2 will then give me 4. Okay, remember this is a compound, so it exists like that. Okay, plus I've left my oxygen, but now over here, because this 2 is going to be multiplied throughout, it's going to be 2 times 2 is giving 4 atoms for iron, and then 2 times 3 is going to give 6, okay, for oxygen. All right, so what I have on this side, I've got iron having 4 atoms, and then I've got oxygen having 6 atoms. Okay, on this side I've got iron having 4 atoms, and then I've got oxygen. How can I make them to be 6? By adding a 3 here, so that 3 times 2 will then give me a 6. Okay, so now I've got iron, we've got oxygen, got iron, got oxygen. Now it is well balanced. What did we do? what did we add? Let me use a different color, black in this case. We added this 2, we added this 3, we added a 4 over here so that it is balanced. Okay, so hope this is an easier method for you to look at it. Start by identifying how many atoms are there for each element, okay, and then work on that to say, how can then I make the atoms on either side to be balanced? All right, now let's dive into, we cannot end a lesson without any multiple choice question, okay, to test how exactly do they ask this chapter in any exam or past question papers that we've used before. So the first question is our multiple choice. I'm going to remind you again how to best master the multiple choice questions. You've got 4 possible answers that are given to you, and then you've got 2 distractors. Distractors because they can never be the answer, okay? And then you've got well, another option that is similar to the answer, very similar, but is not the answer, okay? And then you've got the correct answer. You should be able to have a skill of being able to identify what is there to distract you, okay? And that is just lies on knowing your content, knowing your terms, knowing how to just then get there. All right, so the first one says, which one of the following substances is not a compound? Remember, read what is provided to you, okay, so that you make an informed decision on selecting your answer. Okay, we want something that is not a compound. We're not looking for a compound. We want something from the substances that are provided, the one that is not a compound. Okay, water definitely is a compound because it is made up of hydrogen atoms as well as oxygen atoms that are chemically bonded to one another in a specific ratio. Graphite, that is just made up of carbon. That is just carbon only. Okay, all right. And then sugar, it is made up of carbon, hydrogen, and oxygen. Okay. And then steel, it is made up of an alloy and a mixture of steel, a mixture of iron and alloys. Okay, so definitely cannot be one of the substances that is not a compound. Okay, so the correct answer here, it is B, because it is just made up of carbon atoms only. So it is not a compound like that, because we're looking for a substance that is not a compound. All right, moving right along, question 1.2, still on the multiple choice questions. The correct chemical formula for potassium nitrate. It's similar to what we were just doing, to say then we should be able to move forward given the name, and then we give the formula. Given the formula, we give the name. Potassium nitrate. Do we then know how potassium symbol is like in the periodic table? Or do we not know? Because then that is the key. Do we know our periodic table? Okay, because definitely cannot be A, because there's 3, okay, of the potassium, and then this is not a nitrate, this is nitrogen. Okay, don't even know what that's called. B, no, there has to be potassium. Potassium is capital letter K. Okay, so distractors in this case will definitely be your B and D. Okay, similar to the answer, okay, almost similar is your A, and then your correct answer will be C, potassium nitrate. The correct chemical name for Al2O3 is it aluminium oxide? Or is it aluminium dioxide? Whew. That means there would have been just 2 atoms of oxygen, but there's 3 in this case. C, aluminium trioxide or aluminium monoxide. What did we say about mono, di, tri? Okay, there has to be 3 of the same, 3 atoms of the same element. Okay, 3 atoms of the same element, we're going with C, because it's aluminium trioxide. There's 3 over there. Okay, Question 2. Let's explore long questions now. See, define a pure substance. With the definitions, it's all or nothing. It's either you get your 2 full marks, we hand it to you, or you get nothing. How do you best define a pure substance? Please stick to your annual teaching plan, which I believe all of us have got pasted at the back of our exercise book. Now, a pure substance is a single type of material. It's a single type of material. That's how you get your 2 full marks. Now, write one example of each of the concepts listed below. Which one is an insulator? What do you understand about being an insulator? We know that nonmetals are insulators, okay? They are not good at conducting electricity at all, okay? So, now when we had to give one example of an insulator, we're talking about plastic, we're talking about wood, we're talking about wool, okay? And then if we had to give for a conductor, we know conductors, good conductors of electricity and heat, to be those metals, far left-hand side of the periodic table. Okay, we're talking about copper wire, we talk about aluminum, we talk about steel, okay, any of those ones. And then define the term cation. I always say these are ions, okay, and these ions, okay, they are positive ones, positively charged ones, and they're negatively charged ones. These ones is what we call cations. These ones are what we call anions. Okay, so cations are just positively charged ions. Ions with positive charges. That's it. 2.4, determine the chemical substances given. Determine the chemical substances given. Given their cation, okay? So we want the chemical substances given their cation in CO2. We know to be C4+, okay? This should have been right at the top. 4+, okay? And then an ion in H2O, okay? What is an anion in H2O? Okay, we know it to be O2-, okay? Because also based on its location in the periodic table, okay? Complete the stock notation for the following, all right? Remember the stock notation, we're talking about Roman figures to specify the valency of an ion, all right? So, for iron trioxide, okay, it is important to indicate that is our stock notation in there, okay, Roman figure number 3. And then for 2.5.2, copper chloride, copper 2 chloride, because now it is bonded to 2 atoms of chlorine, okay? Here's our stock notation, all right? Moving right along, 2.6. Now look at the table. It shows a simplified version of a periodic table. Elements are placed with letters A up to I. Let's have a look at this. Okay, so we've got A, B, here's our C, D, E, F, G, okay, H, and then I, and then we have a J here, there. Okay, let's attempt the question. Write down the letters representing the metalloids. Where are our metalloids? Metalloids are also known as our semi-metals. Okay, they are they are in between. Okay, they can behave like a metal or they can behave like a non-metal. They are in between. They're not good conductors of electricity and heat. Okay, but we can make them through doping, but that's a subject for another day. So metalloids will be D and E. Okay, remember they were plated to be yellow, okay, in the periodic table. All right. Now, 6.2, gas used to fill balloons. Ooh, what gas do we use to fill in the balloons? J, ooh, right there, okay, on the J side. Remember what we called these ones? We called them to be noble guesses, okay? Yes, those are our noble guesses. And then a guess found in group 1. What is the guess that is found in group 1? It could be A or I, okay? Here's our I, here's our A. Remember, they were not looking for the name specifically, but they were looking for the alphabet, okay, where we'll find those specific guesses that fill balloons, the guesses that are found in group 1. And this one was very specific to say in group 1. So you had to just dive in there and say, oh, okay, can either be I or A. Okay, moving right along, alkali earth metals. Those are the ones that are on the B. Just to go back a little bit, here is our B over here. These are our alkali earth metals. All right, moving right along, halogens. Oh, we've been speaking about halogens. Where's our K? Right over there. Halogens, group 17. These are our halogens in here. All right, has got an atomic number of 12. This means that we should really know our periodic table. That's a B. That's on the alkali earth metal side. And then has 3 protons in its nucleus. We're talking about our A. If we can just go back a little bit to look at A, where is it positioned? Ooh, there's our A on group 1. Okay. And then the last one, it has the highest energy orbitals, fully filled with paired electrons. Fully filled with paired electrons. These are the ones that we had referred to be the ones that are mostly stable. Okay, these are our noble gases, which are on group 18, where our J and G are located. Okay. Noble gases in period 3, there is our G as well. Okay. Write the symbols and the names of elements represented by B, F, and I. B, F, and I. Let me just go back a little bit. So before we even get B, F, and I, where is then our B? Here's our B. Here is our F. And here is our I. Okay. So they want the symbol, they want the name of these elements of the periodic table. So that is why we said for B, it is where magnesium is located, okay, and its symbol is Mg, and then we've got carbon, okay, its symbol being capital letter C, and then with our I, right at the top, it's our hydrogen with the capital letter of what? Of H. So this activity just speaks to understanding the periodic table, how to read it, okay, how to understand the names that we refer to the groupings of these elements, okay. Then the 2.8, define the term diatomic. Di, what did we say it means? We said it means 2, right? So what does diatomic mean? Molecules that contain 2 of the identical atoms, okay. 2.9, which letters can be identified as diatomic elements? Ooh, we can identify the ones that are the halogens mostly, okay. IFK, that is where we find our chlorine, where we find our the fluorine, iodine, those, all of them, because now we just had to identify with the alphabet only. It will just stick to I, F, N, and K. Okay, but you'll get your iodine, okay, why is my mouse moving? Your iodine, your chlorine, your oxygen, all of them will have your, because they belong as the diatomic material, or rather elements. Now, this is question 3, but before we even get into that, let's check if we are done. All right. this is question 3. Now, based on what we have done today, I'd like you to just attempt in doing it alone now to see if you have best understood the concept of pure substance, the elements, the compounds, okay? If you've best understood the cations, the anions, their formation, if you did understand how we give names to the compounds, okay, the rules that we would rather follow, okay, also to how then these compounds dissociate, they ionize in water and form the ions, cations or anions, okay. So it says question 3, the diagram below shows 3 different substances. There is P, there's substance P, there's substance Q, and there's substance R, okay. Now with substance P, they're both dark shaded, okay, and then substance Q, there are different patterns that exist on 2 balls. So these balls are similar to one another, but that one is different from the other 2, okay. And then we've got substance R. Substance R has got a mixture now. It's got these bonded to that one in a specific pattern, however, and then there are balls that are similar to one another still in the same substance, okay. So to give the keys on which ball is what, so we've got sodium here, okay, that means here is our sodium, and then we've got hydrogen, okay, hydrogen being dark shaded, that means this is our hydrogen atoms that are bonded to one another, okay. We've got carbon, here is our carbon in here, okay. We've got chlorine, okay, here's our chlorine in here, here's our chlorine in there as well as in there, and then we've got our oxygen, okay. Now based on this diagram that is being given to us, okay, then we need to answer the following questions. Now, for 2.1, we had to distinguish between the element and the compound, okay. What is it that you understand about the elements and how is it different from a compound? Then you use the diagram and the keys above to answer the questions that follow, all right. Write the letter that represents the following, the element, okay. From that diagram, which one is an element, which one is a compound, which one is a mixture, and then give the molecular formula for a substance P, okay. And it's easy now because you've been given the names, or rather the key to the names of these substances, okay, to say, okay, a certain ball designed in this way represent this specific element, and this ball designed in this way then represent the specific element. And if then these 2 balls are chemically bonded to one another, you can just simply tell what kind of a compound exists, okay, or is formed due to the formation of the chemical reaction between the 2 elements, okay. Now that is how then you're going to be responding to 2.3.1 and 2.3.2, so that it's easier to give the molecular formula, okay. Last one says, how many protons can be found in 1 molecule of substance Q? How many protons can be found in 1 molecule of substance Q? Just for 16 marks, you're just testing yourself if the content for today was well understood by you and I, okay. Hope you had a fantastic lesson just like I did. I'm going to end today's sessions by quoted by Benjamin Franklin. He once said that an education is the best investment with the greatest returns. Education is the investment with the greatest returns, not the returns that you'd see immediately. However, in the long run, you should see all what you've been investing towards all of these 12 years that you're spending in your primary school as well as your secondary school, okay. Have a fantastic time. See you next week with another lesson on oxidation numbers. Bye bye.